Okay, I have 6 o'clock. Give me a green circle if you can hear me. Nicholas, can you hear me? How about you, Tamolin? Okay, I'm still missing Tamolin. Okay, well, we'll keep an eye on them to make sure they're really there. And we shall begin class. Usually, the reason I'm always a little bit not late, but when we start, I take a couple minutes is I don't have, my office is very close to a church, and the church has bells that they ring at a couple times a day. One of the times is 6 o'clock. And so I can barely hear myself think when they start ringing these things at 6 o'clock. So I sometimes have to wait till they're done. I've also been having some trouble with the graphics on this particular PC. If I disappear from you, I'll make every attempt to come back, but it could take as long as me having to reboot the machine to get back. So, don't worry if I disappear. I haven't gone anywhere. I'll try to come back. If I can't come back, we'll figure something out. Okay, last topic. What was the last thing we were talking about? Somebody raise your hand and tell me what we were talking about in here last. Frank, what was it?
We were kind of going over the 555 timers, and as a leaving note, you asked us to view the schematics.
Okay, Frank, I didn't hear you. Robert, could you give it a shot?
We were going over the 555 timer.
Okay, 555 timer. Okay, Frank, try it again. I think it might have been a setting on my machine.
Yeah, I think I might have accidentally missed the microphone, but yeah, it was the 555 timers.
Okay, great. That's what I was hoping we had done last, and that's what my notes say, but you never know. Sometimes I get carried away and move off topic. So let's go and talk about the 555 timer again in just kind of a review way. Actually, what we should also talk about first is the syllabus tells me that we are roughly here at sequential logic and flip-flops. We've been moving along about 1 unit per class. Now, the next section from here down to the VHDL won't always match that schedule exactly. There are additional topics which I sometimes insert here when I have a particularly good class, and this class is a good class. I would expect to see some of those. But when I do that, sometimes I drop some of the material or simplify some of the material that's here. But what that also tells us is even if that were class for class, we have an exam coming up in about 2 to 3 weeks, depending on which classes I combine here and which classes are unique to themselves. Some of these don't take a whole session, so I know they get combined with other things. But the first exam is going to happen in Unit 16. We don't look like we're getting close because we're only Unit 9, but this is not really much more than a couple of weeks' work. So beware of that. Now, before the first exam, before exam 1, we actually have exam 0. Exam 0 only takes about 10 minutes. And what it is, it's a practice to make sure that you're going to know how to do exam 1, that you're not going to submit something that can't be graded. So one of these nights we have in here, we'll do the exam 0. It really has questions on it for you to answer, but only a handful, 3 to 5 questions. And then we'll go through the process. First of all, how do you identify which test is yours? Everybody has a different one. Second of all, where do you download it? Third, once you've downloaded it, how do you fill it in so that you can use automatic scoring on it? And then finally, how do you submit it and verify with me that I received it? So there'll be a number of steps, and we practice that one time before the first exam. That way, you can be reasonably sure you're not going to lose points just because you didn't know how to submit the exam. Anybody have any questions about the course up to this point? Robert?
It's kind of the opposite of what you asked for, but more beyond this point. When do we get to start playing with these Uno R3s? I'm dying to crack it open.
Well, please don't die on us, and it'll be down in the MCUs down here when we get working on those. Now, one of the things that we want to also pay attention to is on exam 1, we're not going to cover VHDL on the exam. That will be on exam 2 with all these other architectures. So there are a couple topics we will do before we get to exam 1, but they will not be any questions on that first exam about them. Those questions will be here. That gives you a little time to study for them, because in theory, we could have this class and that class on the same night. And in the summertime, particularly when I have, 4-hour classes, and there'd be no way you could study for that and then be prepared on an exam. So I usually drop the last topic. Down here, I don't, because I guarantee we have enough time between the 8088 and the exam too. But there'll be a couple of things in here we may or may not cover that don't show, and we won't do VHDL on the exam. And we'll talk about what that is when we get there. Okay, I've been looking at participation grades so far. There are quite a few of you that have very good participation. There's a bunch of you that are still trying to, log in and record everything and then go away and try to listen to the recordings. Guaranteed you will learn things out of order, and sometimes I teach things wrong the first time because I want you to understand it, and second time I teach it, I clean it up. So you be very careful if you're doing that. The other thing is that if I can't talk to you, I reset your user ID. And so if I, say, Peter, where is your blah, blah, and you can't answer me, you say, I don't have a microphone. Well, if you don't have a microphone, that's a serious problem because you can't participate without one. Get it with the school, let the school figure out how to get you a microphone. If you're not there when I ask you to participate, well, obviously you'll lose points on that. If you never volunteer to answer questions, you're definitely losing points on that. If you volunteer all the time and then answer without the right answer, you're losing points. If you just stick your hand up, that's not really participating. You have to stick your hand up, be called on, and have, a correct answer when I call on you. So just be advised that, don't play games with me. Don't do that. Also, in anticipation, because it always happens, of somebody perhaps not following all the rules on the first exam, make absolutely certain you understand what you can use as resources and what you can't. For example, I guarantee you, if you went out on the web, you'll find something that can make IEEE 754 floating point numbers like a calculator thing. You can't use that. If you do, you'll get the right answer, but you won't be able to show me your work. And if you don't show me your work, if I ask for it, that question is wrong, even if you wrote down the right answer, because would be an illegal activity to use something like that. You can't use somebody else or somebody else's notes. You just think about, how can I best be tested in a class where the teacher can't see me and where it would be very easy for me to cheat? Well, this teacher's been cheated on before and caught a lot of people. I don't catch them all, but I'm pretty good at it. And you don't want to be that person. First of all, if I do catch anybody cheating and it's a serious infraction, I have no choice but to turn them over to the academic affairs group at the school. And way too many people have been dropped out of school because of that. But I can't help it. They make me do that. For things that I can deal with, because I don't think it's a serious enough infringement, I will deal with it. But don't expect it to always fall in your favor. It won't. It's going to be what I ask you to do. You following the rules? Great. You're not following the rules? We'll have to deal with that. Anybody have any questions about academic integrity? Do you know what it is? Okay, just an example of this. Everybody has different exams. In my summer class, I had 3 people that all lived together and were taking the course. They, during the exam, copied each other's answers. which was kind of significant because some of the answers were things that you wouldn't ever think of if you hadn't been asked a particular question. So they put down the answers to one test on a second test and on a third test so that it didn't match the question. You know, write down the word dog, right? And they write down dog on one where the question was write down the word cat. They wouldn't have even thought of the word dog if they hadn't been cheating. And they all confessed to it and it was dealt with. But don't be that guy. And I don't want to really have to talk much more about that. Okay, what was I talking about? I want to talk about this today when the test kind of to anticipate it. The exam is not hard. If you have an accommodation for it, you get your accommodation. You know, don't have to take it. I mean, I do have people that don't do it, but if you have one and you want to, okay, as long as it doesn't lead to you, you know, for example, some people will have an extension to when their exam is due. It is due twice as long, perhaps, as everybody else, but that means you'll have only from the beginning of the exam until afterwards, you know, one exam in time. But during that time, people who finish the exam might be talking about the answers. So clearly you could talk to one of them and find out an answer. However, we take that into consideration. If you cheat like that, we'll catch you. And we don't want that. If you have an accommodation, you can take the accommodation. And I believe in here, all the accommodations on the exams have to do with the length of time you have to complete it. And I give everybody in the class more than enough time to complete the exam. So that's the only thing I can think of. If you have any questions about that, talk to me, you know, after class some night, and we'll see what happened. But don't just check with me that I know you have that. If you gave me an accommodation sheet, I know about it. If you didn't give me one, you better have one in before the exam, because then you can't have the accommodation without it. Dante, you have a question?
Yeah, my question isn't in regards to the accommodation. My question is more in regard to the actual exams formatting itself. I was more curious about the expected question count and actual like time period we have to complete the exams.
Question, that's not a bad question. We'll talk about that more when we do the practice exam, but there could be multiple choice, multiple selection, true and false, fill in the blank, essay type questions. Generally, I give you a couple minutes per question to finish the exam, and then at the end I add some percentage based on past history of how long it has taken people to complete it. Most likely on the first real exam after the practice one, I'll just give you the entire evening. So you'll have from 6 o'clock or 6:05 whenever we get the exam started until class is over at 8:20.
Gotcha. Okay.
Can
Thank you
I
very
answer
much.
your question?
Yes.
Yeah,
Thank you very
and
much,
the type of question may be different per person. Somebody may have all true false questions. Somebody may have matching questions, and it could change on the next exam. And, you know, don't count on the question even being similar in content. They may look almost identical, but one word can change with the actual answer. You know, so I might ask you something about a resistor problem, and in one I'm asking you for the current, and the other I'm asking you for the voltage, but all the numbers that are printed in the question look the same. So be real careful about that. Frank, is your hand still up, or did you have a question?
More just a comment. I know we haven't been able to get together and actually practice a lot of this stuff. For anyone who seems to be struggling with the circuit section of this class, I highly recommend you get a breadboard. They're really cheap. You can get them on Amazon, and they're only like $5 to $10 depending on the complexity that you get. You can actually practice all the different problems we're doing in class in an actual setting.
Okay, well, thank you for that comment. Mohammed, did you have any comments?
Yes,
Questions?
Professor, are we going to have a review day, like where we just review the main things that we'll be having on the exam one?
I wasn't going to have one. Would it be useful?
Definitely.
Yeah, give me a green circle if you think a review would be useful. What if I had the review on a different night? What if I had the review, for example, on a Tuesday evening, so it wouldn't take away from class? Would that still be useful? I realize some of you work and wouldn't be able to be there, but okay. So I'll try to work something in then for a review. Believe me, I'm more concerned with people learning the material than I am with trying to catch you on questions. I know I can ask questions you can't answer. I try not to do that. That's not my goal. My goal is not to flunk people. My goal is to get people to learn the material. That's why it annoys me when people use a calculator, because they missed out what they were supposed to learn. It's not that they get the right answer or what the ASCII with even parity is. It's that they know how to get it. Given a different situation, they could do it. That's going to work in a job sometime. Being able to use a calculator, anybody can do that. And obviously, most of this stuff, somebody did it before and you can look it up. But on the other hand, you may be the guy that invents the next big thing in computing. I have a ex-student in the class that was in this, well, he's in all my classes, but he actually has done quite a bit of work with the ring security system, bringing a lot of things into that they wouldn't have had if he hadn't, basically paid attention in class with me. And he does a really good job of it. It's a very high-paying job, and I would expect others among you to reach that goal. Be able to take what you learn here and apply it, not just be able to parrot back an answer. That's just dumb. Why take the class if you do that? I don't even care about you in the future if you're going to do that. Figure out how to do it. It's the how that matters, and how to take that same thing and apply it to a different problem. Sargun?
Professor, are we going to have any kind of group projects or presentations with the final exam?
Well, we don't know about the final yet. Let's see how far we get.
Okay.
Okay, we'll see. We'll see how far we get. Sometimes we do individual projects for the end of the semester in this class. Sometimes we do it as a group project where each person contributes something. And, that has a good side and a bad side, because the good side is everything that somebody committed that worked will all work together. But then you get the one guy that doesn't do his work, and then everybody loses points because they didn't do the job. That's the way real world is. If the guy that knows how to launch the rocket never launches the rocket, it doesn't matter how good you made a rocket. Okay, any other questions or comments before we move ahead? Okay, let us look at, wait, I probably have that open already. This is the innards of a 555 timer, as you recall. Now we should, I'm in paint right now. We'll see if I can write on this. We had two pictures that we were dealing with. One is the inside of the 555. And the second one we looked at was the outside of the 555. So let's kind of combine that in this picture here. The most important parts of this are really this tree over here on the left and how it hooks up to the chip itself. So let's just draw that out on the left-hand side here. I'm going to be a little sloppy in my drawing, but that's just the way it is. Let me see if I can thicken that. So we have a capacitor going to ground. It'll be big enough that it'll be a polarized capacitor. If you notice, the top of the capacitor is hooked to both threshold and trigger. So if we draw this up, this is hooked here and it's hooked here. Now, additionally to that, in the range after we've hooked them together, there are two resistors, one here and one here. The top one is hooked to VCC. The top resistor here is hooked to VCC. The middle of this is actually hooked over here to discharge. Now, I don't have any good way to route it there, so I'm just going to jump over that and head over here to discharge. Now, we're going to take the control pin and we're going to bypass it to ground. We're going to tie this guy to plus VCC. So we're never using that pin in our circuit. And then we'll look, the places we're interested in seeing are, what's the state of this transistor and what's the output at the current time. Everything else is kind of incidental. Of course, ground is here and VCC is there. So when we've turned the device on, we don't really even need this at the moment. When we turn the device on, we're going to get VCC here. Let's say we're working with 5 volts, or 6 volts, because that was easier to work with. And that means that this tree on this side, where each of the resistors is of equal value, will have 2 volts right here, and we'll have 4 volts right here. So when I first turn this on, trigger and threshold are looking at the top of the capacitor, who's grounded, and they say 0 volts. Okay, so currently, the top of the capacitor has 0 volts on it. So if I take 2 volts and subtract 0 volts, I'm going to get 2 volts, which is a positive number, which means I'm going to be pushing this button right here. I'm going to push set. Set means make the output a 1, but since it's inverted, it becomes a 0. So that means we have a 0 on this line right here. And since the emitter and the base are both 0, the transistor at this point is off. Since the transistor is off, that means that the connection, I actually put this in the wrong place, didn't I? Where's my eraser? There it is. It's not hooked here. He is hooked up here. But well, nevertheless, he's going to not have a path from this spot through the transistor to ground. So this is blocked off. Nothing will happen on that wire. But the capacitor will have charged over some amount of time, perhaps to 1 volt. If it has 1 volt, 2 minus 1 is still a positive number. That button stays pressed, meaning this stays off. This goes to 2 volts. 2 minus 2 is 0. We said that it can't literally ever be 0 because these values will have enough noise on them. They're not going to literally sit at that value. Capacitor is charged to let's say 2.1 volts. By the time it gets to 2.1, 2 minus 2.1 is now a negative number. Because it's negative, we release this button, but this is a latch. The value that used to be there, which was a 1 internally, a 0 externally, stays a 0. So this path stays disconnected. Now this whole time, the other guy has been also comparing that same value. And he's not really going to act on anything until we get to 4 volts. So this rises to 3, this rises to 4. It can't be exactly 4, so we'll say 4.1 volts. This guy, 2 minus 4.1, still negative, so he's not pushing the button. But this guy, all of a sudden, if we take the value of 4.1 and we subtract 4, it becomes a positive value. The positive value here pushes the reset button. Pushing the reset button makes this go to a 0, which makes this go to 1. Since 1 is 6 volts, this transistor clearly has the ability to turn on now and gives us the ability to put something from discharge through that. Well, where is discharge hooked? Discharge is hooked through this resistor to the top of the capacitor. So even though this reached 4.1 volts, now it's going to immediately start discharging. And it's going to keep discharging until this is dropped down to less than 2 volts. When it does, this guy actually stopped pushing the button as we passed back through 4 volts, but this guy will push the button again to set it and close off the discharge the moment we get down. So what the output is going to be seeing on it is it's going to see a swing from on to off, on to off, where each of the charging times and the discharging times control what this output is going to be. And of course, this could be 6 volts and ground, so we could turn on an LED with it. What was the actual value that this was safe having on its output, either into the chip or out of the chip? Raise your hand if you remember. It was different than TTL. Remember, TTL was 400 microvolt. Well, actually, on the input side, well, it was output side. It was 400 microamps or 16 milliamps. What was the amount the 555 timer was able to handle? Samir, what was it?
200 milliamps, right?
Right, goes 200 milliamps either direction, which is quite a bit of current. We can do some pretty potent things with this. And that's the general flow of how this works. We're basically charging and discharging a capacitor. The discharge happens anytime this opens up because now it's got a path back out to ground. These guys are simply comparing 1/3 and 2/3 of the voltage to know that's where we want the capacitor's charge to range. Now, there's one odd time. When you first start the thing, it goes from 0 past 2 volts up to 4 volts and then back down again. And as it's coming down, when it gets to trigger, which is 2 volts, it starts back up again. Its threshold comes back down again. There's not nice sine waves like this. It's going to actually follow an exponential curve. But because of that, with the very first period, the first high signal is a little bit too long. So we design our circuits so we don't care about that. But all the rest will remain with the capacitor having a value between 2 and 4 volts. Now notice, please, that when we charge the capacitor, we call this resistor A, RA. We call this other one resistor B. When we charge it, we're charging from VCC through both resistors. When we discharge, we're only discharging through one of them, through B. So charging will take longer than discharging because charging takes 2 resistors, discharging takes 1 resistor to pass the current. And we know that you're going to have more resistance in the circuit because obviously this resistor doesn't change values when we're charging. So we expect the on time to always be slightly longer than the off time. We could make this very, very tiny, and then this would be nearly a 50% duty cycle. But normally we don't do that. We try to keep within the range that the data sheet showed us in that chart because the chip has been shown to operate best in that range. And if you needed 50%, there's better ways of doing that anyway. You wouldn't just use this chip, you'd use a secondary chip as well. But in this case, what we could imagine is this is on, this is off, this is on. During the time that it's on, it's going to be charging. The time it's off, it's going to be discharging. Charging. Externally, we don't see those signals anywhere that's going to matter because we're going to see it as though it's a rectangular wave. It's not square because they're equal, the periods are different. Now, when we were talking about periodic signals the other day, we said that the time it takes for that is called a period. And it's going to be measured in seconds. Of course, it could be our fractional, like milliseconds or microseconds or something like that, but its unit is in seconds. If we invert this time, so it's 1 over the total period, we'll just say P here for period, then we're going to get the frequency. Call that F. The frequency is going to be in what units? Raise your hand if you remember what units frequency is measured in. Mohammed?
Farads?
No, that's what the capacitor's value is. The capacitor is measured in farads. That's like ohms, except for when it's acting like a capacitor in a DC circuit. So yeah, capacitor uses F for farads, named after Michael Faraday, as its unit. What do we measure frequency in? Stephen?
Is it hertz?
Yeah, it does hurt a lot, doesn't it? Yeah, hertz, HZ. An older unit we used to use was called CPS, and you may still see that occasionally, which is cycles per second. And hertz is number of these per second, and that's why inverting it works. As long as period is in seconds, we'll get out units per second. Now, we have an on time and an off time. The on time's percentage to the total time is what we call what? What's the name of that? Scott, what do you call that?
Duty cycle.
Yeah, the duty cycle. Unfortunately, can't type on this window. I have to write like this. So the duty cycle. The duty cycle just says how much is during the time when it's doing work. We think of that as being the time we're doing work. Now, we could hook this up either way. We could make the high value turn on the LED, or we could make the low value turn on the LED. Or in theory, if we looked at our output where it's coming out of the chip here, and we hook VCC here, well, actually, let's put the resistor here. We put an LED here. We put an LED here to ground. When this is high, what's going to happen? Let me draw my little arrows. I like drawing my little arrows. I've gotten quite good at it. And don't you guys say I haven't. I don't even know what that thing is. This guy's inverted, of course, on this side. So if this has a high value, what's going to happen? Well, if this were high on one side and it's low on the other, we would think this could turn on. But we said high and high. If they're both high, that means there's not enough value difference between the top of this inverter and VCC to give it a point, well, in this case, LED, a 2.1 drop. So therefore, yes, this will continue to show 5 volts here, but on the other side, 5 volts across this certainly gives us enough. And as long as we have the resistor here to hold back the current, we would turn this on. So if the output of this is high, this LED is on. If the output of this is low, that LED is on. So we can choose one of two to be on based on whether this is a high or a low signal. Of course, we might just do one or the other. Now, one of the things that's interesting about this is that the thing operating the transistor is actually opposite the output value that we have. So when we have a 1 on the output, we're going to have a 0 here, meaning the transistor is going to be turned off. And that this double inversion just takes care of making sure the transistor is turned on or off at the right time. We could have thrown in another inverter in here, but there was no need to, because this is easy to put an inverter rather than a buffer here. And this output is usually available on a latch anyway. Okay, anybody have any other questions about the 555? Now, kind of a simple, dumb question for us here is, let's assume that we had the 555 timer's output. We went through a resistor. We went into the LED. And we came out and we went to ground. Let's assume for a second that the resistor right here is 330 ohms. What color code's 330 ohms, by the way? Try not to look it up. Just remember what's a 3. Mikhail?
So if I remember correctly, would 3 be yellow? Or would it be green?
Take a peek at your sheet. Sargon, what do you think? Robert, what do you think?
It'd be orange, orange, brown, and then either gold, silver, or no color, depending on the tolerance.
Okay, so what you're saying is orange is a 3.
Mm-hmm.
Okay, I'll go with that. Now, let's assume when we hook this circuit up, the LED is too bright. What would I change in order to make it be less bright? Scott, what do you think?
You're going to have to change the frequency of the oscillation. You'll have to make the frequency, it's going to have to be higher.
Okay, let's think about that. That's a good path to follow. Many people will say you need to change the value of the resistor, and that'll certainly work. And as a matter of fact, for the picture we drew here, we didn't say how long the on time was and how long the off time was. All we said is they did this. It was on when it was high, and it was off when it was low. If we make this faster than about 15 times a second, what's going to happen is we're not going to ever see it go out. We're only going to see it being on. But because it's not on 100% of the time, it's not receiving the current it would have been receiving if it had been on the time. So what we're doing is something which is called pulse width modulation, PWM. We're generating a signal in which the duty cycle represents the amount of the total signal that's being applied to the load, which in this case is an LED. Now that's an interesting thing to think about for a second, because it turns out that we don't see things linearly. So if I were to tell you that we were going to dim the thing so it's half as bright as it was, the natural instinct would be, well, we're already at 50% or whatever duty cycle we're using for our current one. Let's use half of that. And that's a reasonable thing to say, except they've done studies of this with people. Originally, the studies were done in music. What they did is they put a person in a listening room, and they put a bunch of violinists in a secondary room where the person in the room could hear the violinist play, just couldn't see them. And then the violinist would play a scale. And the person in the other room would just kind of think about it a second. The violinist would play the scale again, and they'd think about it. Then what they would do is they would have two of the violinists play the scale, and they'd ask the person in the room, how much louder is it? Well, it took up to 10 violins before the person would say it's twice as loud. The body doesn't respond to things linearly. Same thing happens in the case of the brightness. It's not exactly as exaggerated, but we're going to perceive a 50% increase or decrease in the brightness. You could go either way. We're going to percent decrease with 25% change in the duty cycle. So instead of, let's say we're 100%, we're going to bring it down to 25. The person is going to think it's only dimmed the light by half, even though we caused our number to go down by 4. So we will do some work with pulse width modulation toward the end of the semester. But the idea of all we do is in a circuit is reduce this value is for very simple electronics. Usually we would run this at a fairly high frequency so we don't see the flashing. We also don't run it at a low frequency because we can, cause people with epilepsy to kick in a session. But in general, we want the thing to be kind of animation speed for most lights. And we know ourselves that if you've ever played a game and you've been getting 15 frames a second, that's about as low as you can even play the game. 30 seconds, modern times now, we start to complain about it. And at 60 seconds, we kick back and talk about the machine we have at home that can do 120 frames a second. But once we get it enough that we don't see the off times and we make it smooth, PWM basically gives you a full on the LED, and we can control the brightness by varying only the frequency, the duty cycle. We won't really vary the frequency, we'll vary the duty cycle of the device, like a 555 timer that's producing the pulse wave. So that's one of the uses of a 555 timer. Anybody have any questions about that comment? Okay. Let me close this for the moment. Minimize that. Go over here to the well. Okay. We're looking at the top part of the picture here. If I'm lucky, I can get it to fit. Amazing. Oh. Okay. Let's look at the circuit labeled A, the one on the left. Notice that one of the transistors is gray and the other one is white. We won't worry about that for the moment, but we'll look at the rest of the circuit. The real question we have is, and maybe we can use that gray indicator to indicate something, well, actually we will. This and those are just opposite each other, and the only difference is which one's colored gray. I just turned this circuit on. Let's assume that gray means the transistor is turned on. After I turn the circuit on, which of these two pictures is going to be the way the circuit is configured? Kind of make some sketches on a little piece of paper if you have to think about it. Think about it. We're trying to decide if when we turn this on, apply 5 volts to it, is that transistor the one that's going to be on, or is that transistor, assuming that there's just two pictures of the same circuit? And we'll take a vote here in a minute. Think about where current has to be flowing. Think about who has enough voltage in order for their base to be energized, which means that one would be on. Just kind of do an analysis in your head. This is why we learn about transistors, is because we can move away from a circuit we're familiar with to one we're not, and we can make some statements about it. Okay, give me a green circle if you think it's A and a red circle if you think it's B. And everybody vote, because I'm taking attendance as well. Okay, at least everybody says they're in there. Boy, we didn't get many people voting for the number one there, did we? Andrew, why do you think it's number one? Or A? Why do you think it's A?
I'm not really sure. It just looked the same, so I didn't think it mattered.
Okay. Basu, you also said A. What do you think? Why did you pick A?
In the first time, when I think I thought like both transactions will be on, and I voted for the A anyway.
Okay.
Right.
Okay, well, let's take a look here and think about the problem. If I apply 5 volts here and I move along the wire through a resistor, through a wire, through a resistor to the base, I'm implying that I can have a path for current to flow into this transistor. However, on the other side, I have the same situation. I can cause current to flow through both of them. Now, if they're turned on, what value of voltage will I see right here? Raise your hand if you know. Mohammed?
Professor, you're saying if the transistor on the left is turned on?
Yeah, if this guy's turned on, what value will I see right there?
0 volts.
0 volts. And if this guy is turned on, what'll be right here? Robert?
Also 0 volts.
Okay, but if there's 0 volts there, and that's tied through this wire to the base of the other guy, that means all of this 5 volts had to drop across the resistor. None of it ever made it to the base. Correct? Am I correct in saying that? Yeah, give me a green circle for correct there. Okay. Well, it turns out that if I were to actually turn this on, and we're just driving current through these resistors here to ground, there really is no ground to go to, right? This guy right here, if this transistor has 0, meaning it's turned on, the only way to have it turned on is if this voltage right here is 0.7 volts. But if it's 0 there, it can't be 0.7 volts here, and vice versa. We see something going on kind of odd here. Well, what happens is, it turns out that this is a stable condition we have here now. But it's only stable because when we turn the power on, we apply 5 volts here, one of them will win. Basically what will happen is, let's say that this guy right here wins. He's going to get 0.7 volts right here. When he gets 0.7 volts there, he's going to pull this to ground. And this being ground means this guy's going to have ground here, which supports the idea that he's off. And if he's off, he's going to have basically 5 volts here, which we'll call a 1 in the future. But so if he has 5 volts, the 5 volts supports keeping this on, because the drop across this will maintain it at 0.7. This guy will maintain this guy at 0, which means this will be a 0, meaning if that's a 0 and this is a 0, this transistor has to be off, leaving this at 5 volts. So when we turn it on, If this guy is able to get turned on first, he'll come on, this guy will go off, and they'll stay in that situation forever. But of course, we could have turned it on and it could have done this instead. This one could have come on first, which would have supported the idea of turning this one off. And if this is off, it supports the idea of leaving this one on. So the correct answer to that is neither red nor green, that's yellow, which is both are true. We don't have any idea which one, but either A or B is going to come on and stay on. And it comes on in a stable state. Once it's in that state, it can't be changed. We would normally have one spot, we call it Q, where we, and it's probably just off the screen here, where we actually look at the value. In the case where this guy is on, we have 5 there. That's a 1 in terms of ones and zeros in terms of logic. In the case here, this guy is on, but because he's on, he's pulled that to ground. This would be a 0 here. So Q is a 0 if it comes up this way. Q is a 1 if it comes up this way. And in fact, in real life, we don't know which one's going to happen. Does that make it sound useless? Give me a green circle if that doesn't sound real useful. Yeah, you're correct. That isn't really useful in that state. What we need to do instead is at the bottom of the screen. We need to set it up so that while the top part will come up randomly, we have 2 wires which will help us change it to another state. Or if we invoke one of these signals and it's already in that state, leave it in that state. Now, do you remember in anything we've been talking about where there was an S and an R showing? Any circuits we've used? Frank, what do you think?
Well, we just used it in the 555 timer, the set.
Absolutely. Absolutely. We actually had 2 R's, but we didn't use one of them. We have a set and a reset. So let's work our way through what would be going on here. Let's first of all assign Q a 0. You know what? I wonder if I can do that. Any of you guys experts at this? Where's my select button? Is it this? I hit select. Can I draw a circle around this like this? And do Control V. Oh, that wasn't a good choice. Do you hit select again? Is that how you do it? Oh, yeah, the problem is going to be it's too big. Okay, I got it. I have to make a smaller version of this for a different time. This guy. But it wasn't this guy at all. We need this guy. There we go. So let's assume for a second that we have a 0 on Q. That tells us about the state of this transistor. Is this transistor on or off? Give me a green if it's on, red if it's off. Yeah, it's on because VCE is really equal to a 0. If we pull that down to a 0, that means Q is a 0. That also means we have a 0 right here. And we have basically no way to make the voltage rise. So there's a 0 right at the base. If this is 0, current can't flow through it. So basically we have 5 volts. I'm going to call it 1 right here. The name of the signal right here, by the way, if we were to write it down, is called Q bar, or not Q. And some of these have them, some of them don't, but it will be present even if it's not brought out to a pin. Now, if this is a 1, that means there's really 5 volts here, and there's 5 volts here, which is great because 5 volts here turns this on, which gives us a 0. So that's one of the states we could be in. This state would be called reset because Q is a 0. And remember in our picture of the 555, it was inverted again, so we made the 0 be the set value. But in our case, it stands for, reset. Now, we can't change that state except we've added these dangling wires here. Right now, we're holding both of these at 0. And let's see how that affects anything. If this is at 0, that's what it's hooked to, so no current's flowing through this. If this is at 0 and that's a 1, some current can flow through that and nothing changes. Let's raise set to a 1. So I'm going to get rid of the 0 and raise it to a 1. If we make that a 1, now current can flow that way through this, and the value here is going to be a 1. Now remember, these are not all 5 volts exactly, but by keeping them 1s and 0s, we don't have to do that incremental math. If he's a 1, this transistor is on. If this transistor is on, this becomes a 0, which is a 0 here, supporting being a 0 here, which means this guy is off, leaving a 1. And the 1 we've gotten from here is going to be supported right here to keep this guy on. So by saying set, I just changed Q from a 0 to a 1. Now notice that if I put this back to 0, this won't go to 0 because it's supported by the 1. It'll just simply go back to 0 here. This will stay turned on. So pushing set turns it on. Releasing it doesn't change anything. Pushing it a second time doesn't change anything because it's already set. And the same can be said of reset. We would do all that same work on this side. But if we make it a 1, this transistor becomes set. Becomes reset. And removing it or adding it back again, once it's in that condition, we'll leave it alone. So our truth table has a set and a reset. Since we have 2 signals, we have 0, 0, 0, 1, 1, 0, and 1, 1. And we have what Q is going to become. If they're both 0s, there's no change. Whatever the output is, it stays the same. If we push reset, Q becomes reset. That's even if we push it 10 times in a row, it stays reset. If we push set, it becomes set. If we push them both, what do you think happens? Stephen?
Does nothing happen? So,
Well, in this particular circuit,
or
the way
depends.
it's hooked up, it's basically going to be the same as turning on the circuit. It's going to put us in an unknown state. But when we release them, we'll release one of them first. It'll be the opposite of that one. So if we release set first, reset is still pushed, it'll go to the reset state. So pushing them both puts them in an unknown state, but it'll be fixed when we release one of them. It'll be wrong, though, if we hold them both set. So the way we chart that is we put like an asterisk over here, which means disallowed. What that basically means is, what are you, crazy? You're telling me to set this and unset it at the same time? That doesn't mean anything to me. So that's a disallowed state. We don't allow the user of this circuit to put a 1 on set and on reset at the same time. Do we really prevent them? Well, we try to build our circuit so that they can't, but if they did, you know, we're not going to all go into a black hole and die. We could, but chances are pretty good that all that's going to happen is it's going to disrupt the circuit until they release one of the signals. And you can't release them both at the same time. One will actually hit ground before the other one does. Anybody have any questions about that? This is a very stable circuit. It has a latched state at the top and the alternate state in that top diagram. We could say it's latched into this because of the fact if this guy is the one that's on, that means Q is a 1. And it's the alternate state is when this would be a 0. But more importantly is the state down here where we're able to trigger using these two guys, one state or the other, maintain it, leave it alone, right? Or it doesn't matter how many times we hit it. And we'll see a use for that. There's actually several uses where you might want to be able to hit a button multiple times and only record hitting it one time. Miguel?
Okay, so if I got the flow right of how it goes, so when S equals 1, it goes through the left transistor, and then flows around to the right, and then vice versa for if R is 1.
That's right. If you understand one side, you also understand the other side because it's the opposite.
Okay, so it's like,
yeah,
it's like
definitely.
inverse.
Yeah,
Okay.
and the same thing's true here. Remember, when the base is high, VCE goes as low as it's going to get. So even though we're putting a 1 on it, the output becomes a 0 because we've turned the transistor, saturated the transistor fully on.
Oh, okay.
Okay, and in the other case, when we put a 0 here, we can't turn it on, so the output becomes as big as it can be, which is, in our case here, it would be 5 volts because that's what we're using. A little drop here, but not enough to matter. Okay, let's move ahead here. What's this doing? Don't save. Put this guy back over here for a second. Okay, we're going to look at the one on the left. Do you remember when I said earlier in the semester, we can make anything out of NAND gates if we try hard enough? Well, this is not NAND gates, this is NOR gates, but if you got a sneak peek over there, those are NAND gates. So what we're looking at here is a way to build a latch where we have Q as an output. It's inversion, Q bar, or not Q. We have two signals, set and reset. And our goal is, if we push set, we want Q to go to a 1 and not Q to go to a 0. If we push reset, we want this to be a 0, that to be a 1. If we leave them alone, meaning we don't push them, we don't want these to change. And if we push them both, we should get our hands slapped. Because resetting and setting doesn't mean anything. That doesn't mean a thing. Okay, think through and label this with 0s and 1s. Label the condition where set and reset are both 0, meaning this is a 0 here, and this is a 0 here. Let me actually, while you're doing that, let me see if I can actually figure out how to select this. It's on the clipboard, no. Maybe we can just draw it. Nope, that doesn't do it. Oh, it's the sky. It's a lot of work probably for nothing there, but we'll see what happens. Okay. So we've got 0 and 0 coming in. What type of gate are these? You should be able to tell me what those are. They look like an OR and they've got an inverted output. Hermel?
NOR gates.
NOR gates? Okay. Everybody agree with him? Okay. NOR gate looks pretty good here. So we're going to be using NORs rather than NANDs. It makes the logic be positive logic rather than negative logic, but we won't worry about that yet. So what we need to do is let's just temporarily write down over here the truth table for a NOR gate. You know what actually I'm going to do here? A, B, Y. Whoop, not U. Okay, so what does a NOR table look like? What's the opposite of an OR? So that means we should have a 1 here and zeros in all the other places. Double check me there. Okay, so we have a 0 on one side of an equation because here's a NAND gate or NOR gate, here's a NOR gate. So the only rows we're interested in are the top 3 because they're the only ones that have a 0 as one of their inputs. But it also means that if we assume the first one is the 0, we only have 2. So it could be one of these 2 rows right here out of the table. But we're actually concerned with not what our gate is producing, because if you notice this other wire where it comes from the output of the other NOR gate. Okay, well, let's just take and set up a situation here and then see if we can work with it. What if we said we want to initially be in the reset state? If we did, Q would be a 0. Not Q would be a 1. So let's just assume, because we know it becomes stable at some point, let's assume that it's in a reset state right now. If this is a 0, that means that we go back here, this guy has to be a 0. Now, do 2 zeros support it being a 1? 0, 0 makes it a 1. As a matter of fact, the only way to get a 1 here is for both of these 2 to be zeros. Let's keep that in mind. So this 1 right here is going to feed back into this one, meaning that it's going to have a 0 as its output because it won't be 2 zeros, so this has to be a 0. So this is a 1, and this is a 1 because the output's a 1. This is a 0 because the output's a 0. So in this case, where set and reset are both zeros, we seem to be in a stable state. But let's check that first. What I'm going to do is I'm going to build another truth table over here. S and R and Q. So 0, 0, 0, 1, 1, 0, and 1, 1 is our possible outputs. Okay, so we said just now 0, 0, we think either produces a reset state or it produces a don't change state. Let's put them both over here for the moment. So it's either producing, we'll just put R for reset here, or no change. One of those two is happening because it's a 0, 0. The way we can decide which one is, let's look at what happens if we make this be in the set state. So if this is set, and this is not set, because they have to be opposite each other, then this 1 comes back here, and we said there'd be a 0 here, right? Because we're testing the 0, 0 case. And this has a 0 coming back. What did we say about 2 zeros in a NOR gate? Well, that's the only time it has a 1, and it does. So anything else has a 0, and this becomes stable. Because in the 2 cases where these were zeros, Q didn't do anything other than keep its value. We can say that this does not equal Q, it does not equal R, it equals no change. So if S and R are 0, 0, we have no change in the output. Now let's see what happens if we make set a 0 and reset a 1. Let me erase the ones that are here. So we're going to say set's a 0, reset is a 1. Okay, well, let's see what happens here. One of the things we know is that since these have to be opposite each other, right? Q and not Q always have to be opposite. One of the two has to be a 1. But the only way to get a 1 is with a line in the table that has 2 zeros. So this guy can never be a 1 over here because he has a 1. So the only way I can get a 0 here is to put a 0 there, which means his output has to be a 0, which supports the notion that anything else gives me a 1 over here. And that 1 is reset, or not Q. So this is the reset signal. We could either write it as reset, or more likely we'd write not Q, and just not say that. Which means this other guy down here is probably going to be the way we do a set. So let's go make them do their thing. We're saying that intuitively, it makes sense that if we leave this at 0 and we push set, and one of these has to be a 0, the only one that can be is this guy. So he has to have a 0 here to produce a 0 there. No, I'm sorry, to produce a 1 there. I said that backwards. If there's a 1 there, that's going to put 2 1s on this guy. 2 1s give me a 0. These are indeed different. And because they're different and Q is set, this holds true. So if we do nothing to set and reset, there's no change. If we push the reset button, no matter how many times, Q becomes a 0, not Q becomes a 1. If we push set, no matter how many times, set turns on and stays on because Q will be, or not Q will be off. We then have the last case, which is turning them both on, and we already know that if we try to set both of them, meaning this is a 1 and that's a 1, there's no way for us to get a 0 over here. Because to get a 0, we have to have, you know, the case where we have 2 zeros in the input. We should say a 1. There's no way to get a 1 over there. We have to have 2 zeros. So this, again, is going to be a disallowed state. Now, the name of this particular circuit is called an RS latch. Yes, I know we call them SR over here, but RS latch. When we do say the words out loud, though, we normally say set reset latch. Little oddity. That'll make you pass your interview quicker also, if you know that. Is that although it's called a set reset latch, we normally call them RS latches. This is its truth table right here. Now, we also can build the same thing. Oops, it's not on the screen, but it's over on this guy, I guess. Using a NAND gate. Now, you can try this one on your own. What I'm going to warn you about is the signals are inverted. So pushing reset may mean taking it to 0 rather than raising it to 1. Same thing with set. You may take it to 0 to mean set as opposed to 1. You probably will be disallowed the 0, 0 state. But I'll let you work with NAND gates. I'm not going to use them again, I don't think, this semester. But you should know it. Maybe your test will use them. Anybody have any questions about the RS latch? All right, let us move ahead. Okay, here is an application of an RS latch at the top. We have a push button which is tied to ground. It can either go to start or it can be put on clear. We're going to take two NAND gates. We've drawn them as the De Morgan equivalents. And we're basically going to cross couple them just like we did in the last picture. Now, because I don't want to give away the truth table for this, because if I do, I'm giving away the last problem. Let's just say that when this goes to clear, basically when we ground clear, clear will become a 1. Not clear will become a 0. When we put it back at start, clear will become a 0. Not clear will become a 1. Notice we can't push both buttons at the same time because there's only one button. So we've gotten rid of the disallowed state. That means if I leave it pointing at start or I'll leave it pointing at clear, it'll create that situation and won't change. Because we also can't create the don't change state. Because remember in our truth table, it had two inputs, A and B. Over here, we only have one input. But it can be either this or that. Now, in real life, when I have a switch like this, and I click it into one of the two positions, slightly before I get to the position, if there's any static electricity in the air at all, I'll get a couple extra hits on the start button. Okay, well, it doesn't really matter in this circuit because we can't get hits on both of them at the same time. But when we're looking at the gate we have, it could be getting signals that look like this. So let's say that I switch this from start to clear. I could get a whole bunch of pulses before it's stabilized on the fact that I had caused the pin to go clear. Notice that pin 1 would have gone high by going to it. I'm sorry, gone high by releasing it. I'm giving away the other problem, but because I'm releasing it. When I release it, two things happen. Start goes immediately high. There's no mechanical bouncing. This is called bouncing. But clear, as this switch approaches it, gets some lightning bolts on it. So both of these signals are seen by the NAND gates. Now, remember that this is TTL. And in TTL, when we're not connected to an input, what happens to the input? Give me some fresh hands. I've heard these guys way too often. On TTL, if you don't hook something to an input, it's the same as hooking it to 5 volts. So the moment we release start, that pin is going to shoot up to 5 volts. And it's going to stay there until we release it. Again, we release clear. Now, during the bouncing time, we're going to get some invalid signals. So what we want to do is clean up the signals. So what we'll do is, instead of directly taking these into the circuit that needs a start and a clear, we're going to pass through a latch. And notice that the latch, which is the bottom signal, has a very clean edge on clear, very clean edge on not clear. And when they switch again, it's a very clean edge. This process we're doing is called debouncing. We're debouncing a switch. We can do this in software. We can do this in hardware. We also can do it in other ways with hardware. For example, with a capacitor, we could debounce it because it takes a while for a capacitor to charge. But this is the way we might use an RS latch to be able to get something to be debounced. Any questions about this? Okay, let us move ahead. What is that? One day, a bunch of engineers got a hold of the plans for their RS latch, and they said, you know what we could do is we could stick a couple of gates in front of them, and while we have an RS latch over here, we would be able to say, only when the clock is high do you accept the S or the R signal. So it's basically, we're thinking of this as being a controlled RS latch or a clocked RS latch. We can use the term clocked here. We have a clock signal. In this case, it's hooked to basically NAND gates, as is our latch. And what's going to happen is, if we say set and the clock is low, that set signal is not going to pass through over to the latch. Now that serves to do two things. One is it blocks set and reset from ever going over here if the clock is low. But secondly, if we set either set or reset high and we wait for and leave them high, these will change when the clock goes high. So it's a way to synchronize these guys changing with a clock. You know, I want to set up a whole bunch of inputs to be some value, but I don't want to pass them through to the set reset latch until a certain point in time. At that point in time, I'm going to raise the clock. Now, while the clock is high, I have to make sure I don't change the SNR because they would pass right through. This type of clock is something called a level clock. So we can put together a little truth table for this, where we have set, we have reset, and we have clock. The outputs for this are R prime and S prime. Now, when they're using the prime here, they're meaning the inversion, or think about what reset is, and this is the opposite. It's a subtly different way of saying inversion. Normally we wouldn't use it, but since they're using it, we'll talk about it. And then, of course, Q is the ultimate output. So set and reset, as we know, can be 0, 0, 0, 1, and 1, 0. 1, 1 is disallowed. Now, if we're looking at reset and set, if we hold things steady, it doesn't matter what happens on the clock, no change occurs on any of the signals. If we, however, assert reset, then there's two cases that can occur. One, the clock is low. Two, the clock is high. If the clock is low, nothing happens. If the clock is high, reset makes it through. Now, in our case, reset is inverted because we're using NAND gates, but I'm just going to use a reset there, and we'll just keep track of the sign of it in our head. And the same thing happens in the case where we do this. The clock will either be low or it'll be high. If it's low, nothing happens. If it's high, a logical set will occur. So we've expanded the table. Now, of course, we still only have 8 lines in the table because really this line, you know, is 0, 0 with the clock being 0, as well as it's 0, 0 with the clock being high. And of course, down here, this guy is disallowed when the clock is low or when the clock is high. Now, interestingly enough, when the clock is low, they can have the same value. We will disallow them just because it looks in the chart like it's explaining what's going on. But if you think about it, the set and the reset may be being set independently by other circuitry. And the only real requirement is at the point the clock goes high, that they be stable. Before that, they actually could be both on. So while the clock is low, we're not going to call it this way. I'm going to use some X's to stand for be cautious. Because if the clock does go high while they're both on, then we're going to create a disallowed state. So the engineers had a lot of fun with this. They saw us dangling around here, but they left us still with that disallowed state. And the no change state is not particularly useful to us here, other than it gives us a way to leave our buttons when we don't want to be setting or resetting anything. Anybody have any questions about this particular set reset latch? We would call this a level clocked set reset latch or RS latch. Okay, well, the engineers looked at this a little bit. And they said, you know, we could actually do this if we wanted to. We could take and, let me go back to that other diagram. This guy. We could take this guy, and of course, we're looking at the one on the right-hand side, but they're demorganed anyway. And instead of us having 4 states, right, we could have 0, 0, 0, 1, 1, 0, or 1, 1. Instead of doing that, why don't we combine R and S into a single signal called D, which has them being always opposite each other? If S is a 1, R will be a 0. If S is a 0, R will be a 1. The D signal is really RS combined in such a way that R and S are always opposite each other. That also means I can never have the state where R and S are equal. I can never have them both being 0, 0, meaning no change. But of course, I can just leave D however I always want the output to look like. And I also can't have these being the disallowed state. So this is an improvement to this design right here. Now you might say, well, that is lovely. If I set D to a 1, Q immediately becomes a 1. If I set D to a 0, Q becomes a 0, not Q becomes a 1. And so the engineers smacked their hands together, went and had a Pepsi Cola, and slapped each other on the back saying what a wonderful design they had made. The name of this is actually a D latch, because we're not using S and R anymore. So it's called a D latch. What do you think the main use of this is in computer programming, or I shouldn't say that, in designing a microcontroller or a processor? Dante, what do you think?
This is a bit like a guess out of left field, but I imagine it's to help save space, considering you don't have to worry about an R and an S input. You just have a singular input. So it saves you space and
Okay.
in the long run.
Okay, that's not a bad thing. One of the things I will tell you is this and this actually do different things. Think about that for just a second. Mohammed, what do you think?
Professor, I was actually thinking that the top one is a 1-bit circuit and the bottom one is like 2 bits.
Okay, well, what they've tried to do with the top one is reduce the 2 bits down. The 2 bits are still here. They just happen to be after that first inverter. And in that, the problem lies. Here's the problem. When I have D, I can set the output and leave D a 1, it'll stay set. If I make it a 0, Q, and the inversion of Q becomes set. And as long as I leave D not set, that stays the same way. Over here, though, I had a third choice, which was I can get rid of R and I can get rid of S, and Q remembers what it's supposed to be. In this particular little circuit, if D is a 1, Q is a 1. If I put D back to 0, Q becomes a 0. It doesn't remember what it would be. So I literally don't have that don't change state. So in practice, this circuit has absolutely no use. If we wanted to build a buffer, which is basically make Q be able to support more Ds and make it just follow D directly, we wouldn't need all this extra circuitry. So a D latch sitting by itself would be a great trap on a test. Ooh, I got to remember that. But it also does nothing. That doesn't mean heading down the D path is the bad thing. D is probably the most used flip-flop there is, but not in this version right here as a latch. Let's move ahead. I can't remember which one it is. That's 4. Now what have we done? What's different about this circuit and the last 2 we looked at? Remember, we looked at 2. We looked at one, then we went back, and then we came back and looked at a simpler version. I mean, you could just say the obvious and you'd be right about part of it. Stephen?
It's got a clock.
Yeah, okay. This has a clock, very much like the second one, which we had gotten rid of when we went just to the D latch by itself. Now, this one affords us the ability to take D, make it high, and Q goes high immediately if the clock is high. However, if I drop the clock, I no longer have to maintain D. So I've kind of given myself back that facility for D to be able to change, except when the clock is high. When the clock is high, D will pass straight through to Q. And of course, it's inversion. This becomes useful. We would call this a D latch with level clocking, or a clocked D latch. And we'll explain, if I forget to explain what the word latch actually means, I'll do that shortly. But this happens to be level clocked. By level clocked, it means the entire time the clock is high, we're basically gating. Remember how we said an AND gate could have one of its signals trigger whether you could block data or not? This is exactly an example of that. When the clock is high, that's the only time these gates can have an output. If it's low, you can never get the condition on an AND that would cause it to make one of the varying values. So this turns out to be useful as a D latch. As a matter of fact, we use the term for that last picture as a D latch, but we almost always, since we would never use the last one, we don't even have to tell anybody it has a clock. If we say D latch, they already know it's a level clock device. Okay, any questions about this? If I put a signal on here, you could figure out what Q and not Q are. Let's do that. Let's assume we have a 1 here, a 1 here. Well, let me actually move this to where it would be. It would be at D. So D is a 1, and the clock is a 1. What value am I going to see on this the other side of the inverter here? Give me a green for the next few questions. Give me a green for 0 and a red for 1. What am I going to see here? Green means 0. Okay, we'll try a 0 there. Now, if there's a 1 here, that means there's a 1 on that. There's a 1 on that. We know the 1 that was on D is here. It's also here. Now, this guy has a 0 on his inputs. So using a NAND gate, we write the NAND function over here so we have it handy. We've got 1, 1, 1, 0. So the only time to get a 0 out of this thing is going to be if all of the inputs are 1, which in this case they are. So we'd expect a 0 here. Now, in the case of the guy at the bottom, we know there has to be a 1 coming out of him because this 0 and 1 here. So they're opposite each other, which is probably a good thing. We wouldn't want to be passing D and not D through. Now, this guy gets inverted back again, meaning that we've got a 1 coming in this side, and he's going to get inverted again, which means we have a 1 coming in here. I'm sorry. The 0 is after the inversion. We get inverted once to this. So he's after the inversion. He gets inverted to a 0. Now, I'm not going to go through this because this is the exercise I told you to do on your own with a NAND gate earlier. But we know the net result of doing that is Q is going to have a 1, not Q is going to have a 0. And of course, we reverse that, these will switch. But the good thing about it is the moment clock becomes low, neither one of these NAND gates can pass D through. So it would be perfectly safe to put Z to 0, even though it's holding it at 1 over here. So using that blocking circuit is very important that you understand that and that you remember that as a component. Okay, any questions about this particular entity? That is number 5, okay. Something looks different about this one. Well, the clock is in the same place. The inverter thing is in the same place. We invert D. So this is a D something. But right here, we have a high pass filter. This is a capacitor and a resistor. So this is a high pass filter, HPF. Now, when you study, in graduate school, the details of control theory and Fourier transforms and things like that, one of the things you're going to learn day one is that a square-looking wave has a lot of high frequency noise in its edges and almost none where it's level. If you think about taking the derivative of this thing, it's simply a constant, and constants have values of 0 while they're being constant. But as they shift from one to the other, there's a function that describes the derivative function of what the change was. In this case, it's immediate go from 0 to some value. So we reflect that with an upward spike. Takes a little time to charge and a little to discharge, but a spike is what we'll see. It also, because we're centered around 0, it will produce the low going spike, but we'll never see it because it'll be sucked up into ground. So basically what we're going to have is a clock. If you think about taking the clock coming in here and making it less wide, less wide, less wide, eventually we're going to get down to so it's so narrow, it looks like a spike. At that point, this circuit becomes exactly the same as the last circuit. The only difference is going to be that because we've gotten this down to being so small, the rectangular part, we no longer really have this whole opportunity to change D. We only have it at the exact point where that edge was. We call this a D flip-flop. When you use the word flip-flop, I can't have to write that out here probably, let's see. Flip-flop, you're either selling shoes or you're talking about an edge-triggered logic circuit. Things that don't have clocks or have level-triggered clocks would use the word level-triggered or just simply be called a latch. If, however, they're ever called a flip-flop, we're making the assumption that they have a clock and the clock is edge-triggered, meaning it's going to use a circuit something like this to make it happen. Now, one disadvantage of this is hard to fabricate on an integrated circuit chip. So there's other ways to do the same thing, but this is a general purpose idea, and we're building it discrete components. So this would be called a D flip-flop. We know it's edge-triggered, and it's edge-triggered on the high-going edge. Could be the opposite. We could have a clock that did this, and we get triggered on the falling edge. We will see how that's notated later. But it's basically the same thing, except we now have a very precise point in time at which we're going to move D to Q. D is going to move to Q only on the rising edge of the clock. Any other time, it's safe to move D, assuming you're maintaining all of the chips, setup and hold times and all those, propagation delay and all those. But in general, because we're using sequential logic, we know we have to worry about that now anyway. So we could also wire it like this. And what we would basically do is we would add another stage in between the inverter and its controlling flip-flops and what turns out to be another latch. So let me explain this to you because it's a little tricky on the eyeballs. Normally, preset and clear are held high. or low, depends on how we design the chip. Then D works just like we said it did. Every time there's a rising edge of the clock, D gets transferred through to Q. However, if I draw a little line here, preset and clear can be made to work as though it were a latch without a clock. So I can cause Q to become set right now, not with respect to the clock, but right now by raising preset. I can make Q go to a 0 right now. It will not even consider it, overrides the clock by using clear. So basically, I've made an RS latch right here that's superimposed on top of the D flip-flop. So I can make Q change either right now using preset and clear. Again, I have to avoid the both of them are the same, because if they are, I'm trying to make it preset and clear at the same time, and we know that's disallowed. Or I want to avoid, well, I don't want to avoid, I want to leave it at preset and clear as being zeros if I want the D clock over here to actually do its thing. So D can be made to change the outputs synchronized with the clock, or I can change Q using preset and clear and not even consider the clock. Normally I would do that at power on or something to hold this in a particular state until the D clock is ready to be used. So what they call it here, an edge-triggered D flip-flop with preset and clear. You optionally may only have one of these or none of them, but you should be advised that they are available. Any questions about this? Because it's about as big as a D. There's a way to build a D flip-flop with an internal capacitor also. I don't think I have a slide to show you. I might. We'll see. Any questions about this? Okay, well, let's move ahead then. An engineer one day, of course, it's always those engineers, looked at the D flip-flop and said, I remember back in the day when the D was really a J and a K. And you say, no, they weren't. They were R and S. He said, yeah, they were, but I had designed on the bench a circuit that's even better than an RS latch and better than a D for certain purposes. And we say, well, what in the world is that? And he said, it's called a JK flip-flop. Notice we got rid of the R, the S, the preset, and the clear, although we could bring back the preset and clear if we needed to. And we've broken D apart to be a J and a K. And we've made it edge-triggered. It is about as good as it gets if you want to do some fancy business. The D is as good as it gets if you don't want to do that fancy business. Now, here's the way J and K have been kind of set to operate. We have J and K, where they're both zeros. J is a 0, K is a 1. J is a 1, K is a 0. Or they're both 1. Now, we already are scared of this because we know this guy means not change, which is good. We would like to be able to manipulate J and K when we're not using them and have the output not change. But this last guy down here is dangerous because if we set them both, things could happen. Let's go back and look at the others first. What they say is Q will always be what J is if they're different. So we're trying to figure out what Q is going to be. If J and K are different and J is a 0, Q will be a 0. If J is a 1 and they're different, Q will be a 1. And they go, well, this kind of looks like what we used to have. We just look like we put a edge-triggered latch on an RS latch, and the guy goes, well, there'll be no need to do that because I did something even better. Notice these are not 2 input, they're 3 input. We go, oh, yeah, I see what you did there. And what they did there is they cross-coupled back. Notice the output of this winds up going over here. And the output of this winds up going over here, which means we get a new state. It was 0, 0. We now have a state called toggle. Toggle means if you hold J and K equal and you give it a clock, make Q be to what it wasn't. So if it was a 1, it's now a 0. If it's a 0, it's now a 1. So we can make Q change back and forth between 0 and 1 by simply wiring J and K together and giving it clocks. This, of course, is a flip-flop because it's edge triggered. This is called a JK flip-flop. I'll just abbreviate FF for flip-flop. Being a flip-flop implies there's a clock, implies it's level or it's edge triggered. And they may say here, you know, that it's triggered on the rising edge or falling edge. This also could be built by adding some of the features of the last one. So it also has preset, or it also has preset and clear. So it could be made fancier. But this, again, is about as fancy as it gets, with the only real serious problem about this being is this is hard to fabricate on an integrated circuit. It takes a lot of space. Anybody have any questions about the good old JK flip-flop? Okay, there's one more I think we'll talk about tonight. This term is no longer used, although you may see it in literature. They're working on other terms to be used in those two positions. But the idea is one is a controller and one is the kind of a secondary device. And if you'll notice, there is no capacitor and no resistor anywhere. This nevertheless is a JK flip-flop. We will abbreviate this particular type as an MS JK flip-flop, where MS stands for nothing other than meaning it's this one. And again, the edge triggering is a little trickier on this one than it was on the others. There are two stages to this. This is stage 1, and this is stage 2. Notice that the clock is wired into the first stage here as though this were a D flip-flop whose D had been taken apart to a J and a K. Meaning that this is basically gating in with level clocking, J and K, so that they wind up at the end of the rising clock when it drops, because the first stage is based on the rising clock. When it drops, they are basically going to be made available to the second stage, whose clock is on the falling or rising edge of the real clock. So the way we can think about that is when the clock rises, J is kind of transferred in limbo to become S and R. At the point in time where this original clock drops, that means the secondary clock rises. S and R are passed through to Q. You might say, well, the second stage still has a high clock. If S and R change, then won't they affect Q and not Q? And the answer is yes, they would, except they can no longer change because the first stage had its clock dropped to low. So J and K can only pass through while the first stage is high. At the point where it goes low, which gives the second guy a high clock because it's inverted, we can no longer change S and R with J and K. We can only cause S to become Q and R to become Q if that's what we're trying to do. Of course, if they're the same, we get different features. Now, notice again, the last stage is toggled all the way back to the beginning so that if J and K are both ones, we get a toggle out of the outputs. So this is a true J and K, just like the last one, but we did not have to fabricate the capacitor or the high pass filter. In this case, it's caused only because we only latch things on this one instance when the clock changes from the first domain to the second domain. Now that's a little bit problematic in how we call these. Normally we will just simply call this an MSJK flip-flop, and we'll be happy to know how it works. But we have to be a little bit careful with synchronizing it with other flip-flops. Notice all the others, if we had a latch, it happens on the rising edge. If we have a D flip-flop and it is or a JK, it's not one of these, it happens on that rising edge as opposed to the whole time level it's high. On this one, it's the same as having two clocks. We have the original clock, which went high, and we've transferred J and K to S and R. But we have a secondary clock, which is low, goes high at this point, and stays high. And during this point here, if S and R were to change, they would go to Q. So in fact, this looks like, if we look at the primary clock, that the actual flip-flop is low going. So on this would actually latch the data on the falling clock. Even though talking about it, what we would see is the falling clock here causing a rising clock in the second stage. So we may have some naming convention problems. More likely we're going to have, when we draw schematics of it, we're going to have to remember that this guy almost always is on a falling edge, no matter what they tell you. Anybody have any question about this one? We're not going to really poke into more than one other type of flip-flop. And actually, we'll talk about it, but we won't do anything about it tonight. We'll wait until we're working with, a couple classes from now to really focus in on that. Let me move this out of the way so I can see who's in the class. Mikhail, do you have a question?
It's not really a question, but could you go to the previous slide? I didn't finish copying it down.
I'm going to give you copies of these. You don't need to copy them down. If you did, that's good, but I'll give you printed copies.
Okay.
Actually, why don't we actually, while I'm thinking about it, I'm glad you brought that up. Let's download that. It's, where do I have a window? It's this one. So go to the website. See, this is 231. And it's /F_F.zip. I think. Yes. So you go to the website. And then you can unzip that and you'll have all the slides I was using. Don't give those away. These are actually copyrighted and I have permission to use them with my class, but you don't. So, make sure you keep your copy to yourself. Did everybody get that downloaded? Give me a green circle showing you got it. One other type of flip-flop we might run into, but you won't typically see it in the wild just as a discrete component. Usually it's made up inside of another chip where you're using a application-specific type of hardware grammar. But it's called a T flip-flop. A T flip-flop is like a JK flip-flop, but only has one input. So remember, a JK flip-flop has a table that looks like 0, 0, 0, 1, 1, 0, and 1, 1. And it's set Q, no change. Q is a 0, Q is a 1, and this is toggle. Well, a T flip-flop is the same thing as if you tied J and K together. So you can only get 2 lines out of the table. T could be a 0, T could be a 1. Well, if it's 0, that's a no change line. And if it's 1s, it's toggle. So you can either tell a T flip-flop to do nothing, or you can tell it to toggle. You can't tell it anything else. Anybody want to guess what the T stands for? Give me a green circle if you think it would be toggle. Oh, you guys are brilliant. That's exactly what it is. T flip-flop is called a toggle flip-flop. Okay, let us move ahead. Let me think what, oh, we're going to look at a data sheet next. That's what it was. Okay, I just arbitrarily picked for a data sheet. This guy, it's a dual D flip-flop. Positive edge triggered with preset and clear. So it's got all the bells and whistles. Dual, when you're looking at a data sheet, means there's 2 of these devices inside the chip. So this will contain 2 D-type flip-flops. D-type, is it a RS latch type? Is it a D? Is it a JK? Is it a T? This tells you which type of flip-flop it is. It's triggered on the rising edge, meaning it has a clock on rising edge. It is a flip-flop, which also tells us it's edge triggered. And it also has the asynchronous preset and clear, meaning they're not hooked up to the clock, but they override any normal behavior of the D pin. And here's the internal 2 views of 2 different packages it could be in. We would be using a 7474 to match what we did in class last time. Some of these notes have the extra things. This is a low power Schottky. This is just a Schottky diode package. Up here are the military grade things. We're using the N package. So the N package is the 74, is the guys that right here. And here's what's here. The little 1 means it's on part of the first flip-flop. So first flip-flop's not clear signal. The first flip-flop's D. First flip-flop's clock. First flip-flop's preset. Notice that preset and clear have inverters over them, meaning that to make them do their thing, you take them low. You normally leave them high. Here's Q, not Q. Here's the ground for the chip, VCC for the chip, and here's all the stuff for the second flip-flop. And then blah, blah, blah if you wanted to see it. But here's the truth table. D is the last column here. Doesn't matter what D is or what the clock is doing if you use preset and clear. Preset and clear only have 3 valid states: low, low, high, low, and low, high. If they are held high, they don't do anything. Okay, so in the case where they're being used in this circuit, it's the same as if they were in a disallowed state. You can't do preset, you can't do clear, you're just not using them. Notice that in the case of low and low here, you're telling it to do both of the 2. Over here, if you were to read the note below, it says you're going to get a high state temporarily, but when you release one or the other, it's going to fall back to the disallowed state. So while it's illegal, it does something rational. Over here is our clock and D. They don't do anything if preset and clear are used. However, on the rising clock, if D is high, Q becomes high, not Q becomes low. On the rising clock, if D is low, D passes through. If the clock is low, then it doesn't matter what D is, it stays the same. Q sub 0 means what I was. and not Q remains the inverse of that. There's some fancier logic symbols down here. We don't need to look at those. This one is probably would look more like what you'd be used to seeing, but because they're using 3 input things, they become a little harder to read. Some internal how the circuit is actually wired up. We're not, on this date, we're not that worried about it. It says the maximum supply voltage could go as high as 7. Typically on the 74 with no thing, it's about 5.5. Some temperature stuff we don't really care about right now. Then the data we do care about. So we're in the second column, 7474 here. Minimum is between 4.75 to 5.25, same as the regular TTL. We're guaranteed to recognize a high for input all the way down to 2 volts. We're guaranteed to recognize a low all the way up to 0.8, which was part of the problem if we were trying to hook up to a transistor. Our output current, 400 microamps here, or 16 milliamps if we're a 0. Now, these are matter. If we want to pulse the clock, in order to go high, has to be high for 30 nanoseconds. It has to remain low for 37 nanoseconds, which are going to set an upper bounds on how fast we can cause the thing to toggle. If we're going to use preset or clear, we have to hold them low in order to make them work at least 30 nanoseconds before releasing them. This is called the pulse duration of those particular signals. Now, let's assume that I'm changing the data that I want. I'm changing D. I want D to be stable when the clock goes high. There's 2 times I care about. Time sub setup, time sub hold. So the input has to be stable for at least 20 nanoseconds before the rising edge. Once the rising edge has reached its high value, we have to continue holding it for 5 more nanoseconds before we can change it. Now that doesn't sound like a lot of time, but if you designed it to change exactly on that edge, it would misread many of the times. Then finally down here we have the electrical characteristics. And you want to, when you look at that, there is some variance. For example, the input high for D is different perhaps than it is for the not clear pin or for any of the other pins. Over here you can see it's 40 microamps. For the clock, or for the clear pin, you actually have to be able to provide 120 microamps. And for the other pins, you have to do 80. So D turns out to be pretty sensitive. We can handle him with very little current. And you can see the same sort of changes if you're looking at the low inputs. You would want to pay a lot of attention to those. Now, there are some other timing things we care about. Frequency max is we can go typically around 25 megahertz. Minimum is 15 megahertz and still be successful in working, though we would be able to go lower than that. This is a minimum if you're doing, toggling at the maximum values there. These are basically the times we need for preset and clear going to Q or not Q, or the times from clock to Q or not Q as a propagation delay. Notice that the time between, let's use clock here. I change the clock from low to high. The output will not show up typically between 14 to 20 microseconds. Could be as bad as 25 to 40, depending on how sensitive it is. You might want to design for worst case scenarios here. And it's a different time if we're changing from low to high than it is from high to low on Q. So the propagation delay with the clock, changing this signal from low to high, is going to be, well, in this case, they're the same. No, they're actually not, because we have low to high here and high to low there. One way it's going to be typically 14, the other 20. So those charts. Now, if you keep going in the charts, what you're going to find is the same data repeated again, but for a different chip. So you have to know when to stop when you're looking at this data. Now, we wonder about that when we're designing a circuit. Let me be this guy. So just arbitrarily, let's assume that we have somehow synchronized all of the clocks in our circuit. And we've gotten this beautiful 50% duty cycle out. So we know it's not coming straight out of a 555, but somehow we've gotten it. And we know that each interesting period here, let's do one more, is going to have some amount of time low, some amount of time high. We know that the total of that is going to be basically the period time, and the inverse of that will tell us how long the thing is. Now, these don't have to run evenly. Normally, we call a clock one that is running evenly, but they don't have to. They could be, I'm going to do a clock for 2 cycles and stop. Later on, and just file this away for later, we're going to call this time period here a T state. The T kind of stands for time. We're just going to use it just as a word for now. I'm not going to explain exactly what it is. But in our T state, the clock signal is going to start low, and about halfway through, or some known time through, it's going to go high. It's going to be that rising edge right there we're going to use to synchronize all our clocks. And what we're ultimately going to do is we're going to use this as the indication of transfer data now. So you can think of some amount of time in here being used up to move something from box A to box B, for example. We're also going to look at all of the control signals necessary for that to happen to have been set over here after a falling edge. So we're going to set up our signals here. Then when the rising gets, because we're going to hold these all the way till we get another falling edge. And we're going to hold this guy all the way till we get a falling edge. But we're going to make absolutely sure that this is stable right here. So A and B could have been changing all over the place right here. These set signals could have been changing all over the place. But at the point where we cross this rising edge, everything must have been stable within the setup time of whatever pins we're dealing with. And they have to be held the time we need, but minimally the hold time that the circuit needs in order to capture the data. So we'll keep that in mind as we move ahead. But the important thing here, and what I want you to get drilled in your head for the moment, is when we transfer things, there's a safe time for things to be changing, and there's a time when it must be absolutely still. We want to always capture it when it's absolutely still. Usually it precedes very slightly this because it needs to have setup time on it. And we know it has to last at least hold time after. But it can change any other time, the signals we need, and the transferred data will remain steady throughout this entire high time. That way, if somebody wants to look at it and say, what's the value, they know only to look when the clock is high, and they know only to look after the setup time for the data they want to look at. And we'll work on that because that becomes critical to designing a processor that it knows exactly where data is and when it's valid and when it's not valid. Okay, there's a couple things we didn't get to tonight that we will get to in the next class, because I believe the next class we're going to talk about counters and shift registers. Let me. Yeah, counters and shift registers. And I'm going to talk about the schematics for a flip-flop, how you draw and how you can look at the flip-flop and know it's a D flip-flop, or know it's a JK with a clock, or know it's an MS flip-flop, whether it's level clocked or it's rising clock, falling clock. And we'll do that probably first. One of you guys remind me of that at the start of class, that I want to do that before I do the lesson of the evening. If we get, let's see, actually, we're going to do this on that class. I doubt we're going to start finite state machines, but if I get through this too quickly, I'm actually going to talk about some of the material that's in this lesson, set of lessons here. Because like I say, this kind of gets compressed a bit, and we may not need all the time to get to this exam. Anybody have any questions or comments before we're done for the evening? We got a couple minutes here still to talk. Okay, well, we actually have 4 minutes, because that's probably going to be enough for me to give you a start on the schematics. In general, we draw boxes which have function as squares or rectangles. In the case of a latch or a flip-flop, we're normally going to put the outputs on the right-hand side. So we might have Q, might have not Q. Now, a particular flip-flop might have both, might have one, might have two. So you could have a flip-flop that only had an inverted Q. So that's part of understanding what the flip-flop does. On the top and bottom, normally inverted, meaning we'll have a little bubble here, we'll have things like preset, and clear. Now you have to be a little careful with these two, because this means it's inverted, but it also would mean inverted if the name had a bar over it and there was no bubble. And some companies do both. They put the bubble and the name, and they still mean it's inverted. So watch out for that, because normally these on the side are inverted, and you would go to the data sheet to find out for sure. Now on the left-hand end are the input signals. If there's two of them, like R and S, one of these would be R, the other would be S. It doesn't matter until you look at the thing to figure out which is which. They could be J and K. This could be J. That could be K. They're normally the inputs. Now, if it's a flip-flop, there's going to be an edge-triggered clock. Clocks generally are drawn either below the first input. In case of a T, there'd only be one input, or a D. And the clock appears as a signal here, maybe labeled inside or outside. We'll put it out here this time. And if it's labeled just like this, pressed up against the box, it's a level clock. If it has an inverter on it, or the name is overbarred, or both, normally it's an inverted clock, meaning that the level is when it's low, not when it's high. And again, you have to look at the data sheet if it's got both signals marked. If, however, it has a little triangle right here, that means it's edge triggered. And the same rules apply. It's rising edge triggered unless there's a bubble, in which case it would be falling edge triggered. In that case, it might or might not have the overbar. So if I drew one that looked like this, it says set. Has a bubble here. What could you tell me about that? Is it a latch? Is it a flip-flop? Is it something else? Put your hand up if you know what that is. Well, there's no clock, so it's not a latch, it's not a flip-flop. It's simply some box that takes in a signal called J and a signal called K, puts out an inverted Q, and has a set secondary function. So you don't really have a good name for that one. We took one. What is that? And a clue, there are no RS flip-flops. Okay. Patricia, what do you think this is?
A level clock RS latch.
Right, it's an RS latch with level clocking, and it has a clear, okay, because clear is one of the asynchronous, so asynchronous clear. You might also note to somebody that it does not have an inverted output, right? It only has Q, it doesn't have not Q. So you can be very descriptive in filling in all the words just from this simple picture. If we needed to plug in the not Q, we can't do it here without putting an inverter. Robert, do you have a question? Okay, well, that's probably enough. We'll go over a few of these at the start of class, but that's the basic. As long as you can kind of think through the labeling, you can kind of identify these. And once we've used a few inside of some counters and some shift registers and things like that, these will make a lot of sense. Important thing here is these happen over time. They're not like the AND gate where we applied a signal and we always thought of it as having an output right now. We need to know something about this one. What state is it currently in? What happens on the clock later, or what happened the last time we saw a clock? So we start to care about propagation delay, hold time, setup time, maximum frequency. So just put your thinking cap on and think about that. Now I would review all these slides because I think they all contain data you're going to want to remember. Anybody have any other questions or anything before we leave? Then say good night to me.
Have a good night.
Good night, Professor.
Night.
Bye-bye.
Good night.
Bye-bye.
Good night, Professor.
Good night.
Have a good night, Professor.
Bye-bye.
Good night, Professor.
Good night.